I would like to introduce the first speakers. Paul Schenheim is with a principal at 50,000 Won Strategies LLC, which assists manufacturers in deploying energy efficiency and clean energy technology strategies. He worked for 30 years at the US DOE Industrial Technologies Office, and his expertise is in industrial heat pumps, pinch analysis, energy assessments, electric motor systems, and the ISO 50001 energy management system standards. He led various teams at the DOE to, for example, develop the DOE's energy management software tools, deploy the Safe Energy Now initiative, and manage the Superior Energy Performance Program. Paul has a Bachelor of Science in Mechanical Engineering from the University of Connecticut and a Master of Science in Mechanical Engineering from Drexel University. And with him, we'll have Jim Kumana, who holds a Master of Science degree in Chemical Engineering from the University of Cincinnati and has over 40 years of experience in process design and energy water optimization, working for manufacturing, EPC and software companies before establishing his consulting practice in 1997, which specializes in process integration, pinch analysis. He's been a consultant to major corporations worldwide, including chemical companies, oil and gas, food and beverage, and pulp and paper industries. And he also serves as a consultant to the US Department of Energy, Natural Resources Canada, World Bank, and UNIDO. He has authored and co-authored over 75 technical papers and book chapters and teaches private courses for process integration in the chemical process industries. So I would like to welcome them to the stage for this presentation. Thank you.
Well, good morning, everyone. Look forward to getting this conference kicked off, and feel very honored to start things off with you. And as was mentioned, there's three of us here today: myself, Jimmy Kumana, and I Meyer. She's from Oak Ridge National Lab, and Senthil Sutamati can't make it today, but what our team is here to present is a new program at DOE that's been piloted that's called the Energy Intensive Industries Program. And we're here to describe what the program is, what the offering is to the energy intensives, which we assume most of the end users, manufacturers here today are from those sectors. But we're also looking for some men and women that could join our effort to support that sector. In particular, people have experience in pinch analysis, process integration, system optimization, and any of the tools and techniques that are used that Jimmy will dive into in a few minutes. We're here to represent the Department of Energy's Industrial Technologies Office, which, as I said, this energy intensive industries program is in the 5, 6, 7 sectors that use probably 60% of the nation's industrial energy, including chemicals and refining petrochemicals. The program also has cross-cutting technologies, thermal and process systems, low carbon fuels, energy emerging efficiency technologies, water, wastewater, as well as the near-term programs, Better Plants. Anybody here at a company that belongs to the Better Plants program? Okay, very good. That's actually why we're here. Was we very few of the energy intensive are part of that program, and we're trying to fill that gap. The on-site energy program, which is here, HARC, which is represented. I encourage you to go to the booth and find out more about that. And the 50,001 Ready program, which helps companies implement the ISO 50001 standard. So this slide describes what the challenge is for us, in that within the Better Plants program, it's mostly the light-intensive industries that are joined, okay? The more consumer-facing companies, right? At the end of the supply chain, where you folks, many companies here, are on the upstream side, and very little participation with the facilities that consume large, tens of millions of dollars of energy per year. So if we look at the next slide, this energy intensive pilot was started in 2022. And this was, the goal was to increase the energy efficiency, partner with these energy intensives, and to really understand where the value was in terms of what DOE could offer to those companies. There's another slide I'll talk about actually what was done. But what we want to do is we want to not only partner with the companies, but also get their feedback of where the value is, where maybe DOE's research should be focused in terms of really having impact. And then what we're going to talk about with Jimmy and we're going to talk about maybe what the program offering is and how we can work with companies that all are similar but yet have different needs. Every plan's different, right? So we really need to get in there and understand where the opportunities are. So did you realize that less than 5,000 of the industrial plants in the United States out of 200,000, so less than 2% of the plants in the United States account for almost 60% of the energy. So we have a really kind of a sweet spot of opportunity here to improve productivity. And many of those, I'm sure many of those companies and plants are here today. So now what DOE did back in 2022 is they engaged about 40 facilities, and they gave technical assistance to 16 of them, and they found $32 million of savings. The kind of things they did was process heating, energy treasure hunt, steam, process cooling, compressed air, pumps and fans, 50,001 READY program, waste reduction, plant-wide assessment. Then they also did a post-assessment survey, and the companies found the most value in the energy assessments that were done, some decarbonization assessments. They also said there's a lack of subject matter experts in certain distillation or various unit operations due to retirements. Maybe you've been seeing that. That's more real to you than me. So we're trying to address that issue by getting folks that are interested in partnering with us to work with the plants. So here what we're talking about is there's a large opportunity, and we're trying to address that large opportunity with the skills gap. And what Jimmy's going to come up now in the next slide and basically talk about the pinch analysis, system optimization, and ways that we can really address some opportunities that are out there by integrating your plant more. And then I'll close it out and talk about specifically what we're offering here in the program. So Jimmy, if you would come up, leave plenty of time. He's the expert here, so we want to give him ample time to make his case.
Okay, so pinch analysis, some of you here are very familiar with it.
Next slide.
Yeah, that's it. But some of you may or may not, may not know much about what it is. The focus of this presentation is just telling you basically what it is and bring you up to speed so you can understand what it is that is going to be offered. Okay, first a quick definition of pinch analysis. It has broadened. The definition of pinch really now is that it's the performance limiting constraint in any system. So you have energy pinches in the process pinch based on energy. You can have a pinch, it's like in an organization where there's somebody who's got an inbox but no outbox, and no decisions get made or they are delayed, and you've got somebody in finance who doesn't understand what's going on, and he says, no, we don't have the money and all that, and they just don't understand it. So a lot of efficiency improvement in the industry is held up because we have people who do not understand what a pinch is, and that's what this slide is about. And if you get nothing else out of it, take this slide and show it to your boss, okay? Okay, so in the process, the basic idea is that I'm just going to touch on a couple of things, very, very basic. It is possible to take all the process streams in a plant which are being heated or cooled and combine them into enthalpy vectors, or what are called composite curves, okay? They're not physical streams, they are heat flows. And if you put them on a temperature enthalpy diagram, you find that they have a certain shape, and then you can adjust how much, you can estimate how much heat recovery is possible economically by moving these curves on the x-axis. You basically start with the hot stream curve, the red one, and then you plot the blue, and you move it to the right until it touches the optimum approach temperature in the system. Now, this is a difficult concept perhaps to understand, but we don't have time to cover it in the slides. I will just mention it, and then if you want to talk further about it, I'll be here today and tomorrow. You can come and talk to me, okay? So the point of closest approach is called the pinch, okay? And that's what limits the amount of heat recovery that is economically possible. Now, if you look at the top of those curves, okay, you see Q hot, and at the bottom you'll see Q cold. Those are the energy targets, and this is relatively easy to do, you know, in any plant. So you collect all the streams and you can thermodynamically combine them, and you get the energy target, the thermodynamic energy target for heating and cooling. And this is valuable information, because if you're doing a whole bunch of energy recovery things and all that, how do you know that it's time to stop, that you can't get beyond this point, okay? Or if you're not there, which is most likely, what is the potential for additional recovery? And that's valuable information for management. Okay, so this is something that can be done fairly easily, and this is one of the things that DOE offers through Oak Ridge in this particular case. Okay, now there's a pinch principle, and that is that once you accept that there is a pinch, you divide the process into above and below, just conceptually, okay? In above and below in temperature. And the rules are, you should not do any cooling above the pinch temperature. You should not transfer heat from a process stream, process heat recovery from above the pinch temperature to below the pinch temperature. And you should not add any heat to streams that are below the pinch temperature. And if you do this, you're almost guaranteed, not almost, you are guaranteed that you will achieve the minimum energy targets, okay? Now here's just an example. The heat exchanger network, which is HEN, is represented in grid format. And this is just one of the tools. Now this is getting past what the offering is. We can offer training in this, but we don't actually do this for you. So this part we will do. This part we will offer you because it's very easy to do, but the rest of it is something that you may ask, well, how is it possible to implement this target? How do you get to this target? And this is how you get to it. You get to it by following the pinch principle. You represent your existing network, and these cross lines that you see on there represent cross-pinch heat transfer, and the idea is to eliminate that so that everything is separated. Either it's all heat transfer is done above the pinch or below the pinch. Okay? So that's as much as I'm going to talk about on the technical side. But in order to implement this now, what you need are good data, which means updated process flow diagrams. There are many plants I've seen where people don't even have a heat and material balance, and this has to be validated. It has to make sure that it's consistent with the laws of nature, like properties data, and consistent with the heat and material balance. You have to get accurate marginal prices for utilities. There's ways to do that. All of these things can be done. I'm just saying that it has to be done in order to have an effective program. You also need to have a relatively accurate and rapid cost estimating tool. Okay, this is very difficult generally unless you go through some software which is available. And you have to have a pretty good idea of the plant layout in retrofit situations, because you cannot combine streams which are very far apart. Okay. So then the next big thing is you have to accurately extract the data. This is, again, it's a technical term. You have to be able to pull out the relevant data and make sure you exclude the things that are irrelevant. And it generally requires a team approach. You have the people who know the pinch analysis method. You have to have good engineers involved, and you also have to have operations people involved in order to make sure that they are willing to operate the plant the way you the way you're proposing. And finally, and most important, you have to have management support. If the management of the company is not for it, and is not willing to support it with resources of people, of training, and of capital for project implementation, then you might as well not start it. Okay, I mean, I hate to say that, but that's the fact. You can do all this technical work, and if the management doesn't support it, then nothing's going to happen. Now, how do you incorporate the pinch design into a project procedure? You have the initial project definition, and you have project management, and generally the project management people will resist doing this because they will say it will delay the project, it will increase the cost and all of that. It isn't true. But anyway, that's the mindset. So this green part here that you see is the insertion of the pinch analysis into the overall project procedure, which is the orange boxes are the normal way of doing it. You should have a short circuit. If you see the dashed line over there, I'm pointing to it here, but it's actually over there. I can't see that. Okay. Quickly, I will mention that there are two kinds of optimization. One is structural. In other words, what is the structure of the process? And then we hold that steady, and you take the existing and then you optimize it on a retrofit basis if that's the case, or a new design, you do the structural optimization. And after that, you follow up with parametric optimization of temperatures, pressures, et cetera, okay? So it's a two-stage process, and what Pinch does is the structural optimization, and what simulation modeling does is the parametric optimization, okay? So there's no point in doing parametric optimization if you don't have the right structure, and that's the message. Now here's some empirical data. The projects that are identified will follow some kind of an S curve, and it's going to, it's showing two. The most of them will fall in between the blue and the red curve that I show here. Now, it's quite common for management to say, hey, I want a 2-year payback. So if you get, say, 2-year payback, then of the potential, 100 represents the full potential for savings. At 2-year payback, you'll get about 20%, maybe 30% of the potential, not of the total, but of the potential improvement. Okay? If you take a 4-year payback, you'll get somewhere between 65 to 80%. And if you take and remember, 4-year payback is like 25% ROI. Where are you going to get that kind of return on investment? Most plants give you only, over the long term, 7, 8, 10%. And if you go for the whole thing, then you can get, at about 7 to 8 year payback, which is around 10, 12, 15%. You'll get all the savings. That's possible by applying optimization. Here's an example for one company, and you'll see that it's a multi-year program. And if it's not supported the whole time by management, then all the work that you do over here is wasted. This is the beginning. This is where you do all your studies and planning and all that. That takes about 2 years, by the way. Okay? Of course, this particular company had 15 plants, so this is a composite of all of those. And then you begin to implement the easy things first, and you come down here. And then by this time you've got all your project approvals and the design is all being implemented, and it drops down and it ultimately levels off somewhere here. In this case, what I'm showing is this is 100% of the potential savings. Okay? So you come, no, sorry, that's not it. This is the actual energy footprint. The energy efficiency index was defined as actual energy cost versus energy cost of the baseline efficiency. So baseline, your energy cost is 100% and is dropping, and in this case it sort of starts to level off right around 50%. Okay? So that's real data. Okay. And the red is actually what happened, the blue is what was projected. Okay, so back to Paul.
What do you say here?
Okay.
So that answers some questions, right?
Is this something you would offer to plants like in the design stages or only operating plants? Because I think from Savic perspective, we found we have more success putting in changes and things at the EDP stage or earlier in getting things implemented or design versus waiting until.
I would say both. Let's just have a discussion. We're still at the early stage of the program, so we're going to be in a learning mode. If we partner with a company, we're wanting to learn what your needs are, where you are. We don't pretend to have all the answers right at the moment. Every plan is different, every company is different. I also think I would say is we're going to be very flexible to work at the facility level or the corporate level, okay? We realize that, there may be situations with a company has an energy program, and sometimes things start at the grassroots at one particular facility, and then we'll go, to across the company. So we're okay with working with one facility or the corporate, either one. Any other questions? Good question.
So I was just wondering how accurate is the pinch analysis? Is it always 100% accurate?
It depends on what you call accuracy. Okay? It's thermodynamics. If you do your calculations correctly, it's 100% accurate. If you don't do the data extraction and get your marginal cost prices right and all that, garbage in, garbage out.
It's only as good as the data you collect, right?
Absolutely.
Yeah, so final question. So do you people also, do pinch analysis with academia, or is mainly on industry?
Industry.
Okay. Okay.
Okay. Yes. If you are in academia and you have an interest in pinch analysis, we'd like to talk to you. We feel long-term wise, this has to be taught in schools, engineering schools. Okay. If you go to Europe, you'll find there's many universities that teach this. There are a few in the United States. UC Davis currently has a program where they teach the engineers pinch analysis. There's a couple other ones.
Rice University does.
Yeah, there we go.
Rice.
Kudos to you. So we'd like to know that what you're doing. Please talk to us. Hear what you're doing.
Okay, time's up. Let's try to move on to our next speaker.
Thank you.